Let me stop the timer. It is 4:30, so we're going to get started. I'll give you a couple more minutes on this one. If you're still coming in, you'll have a few more minutes to work on it. So last class, we were doing compound interest, and we were in the middle of the derivation, and we ran out of time. So I gave you guys the final formula. The final formula for compound interest is this formula. So in this class, we're going to finish off the derivation. That'll be the first thing we do. We're going to finish deriving the formula. We were halfway, and we had this nice picture of a calendar. I'll go over that in a second. We're going to fill in the second and third period to get to eventually this formula. That's what we're going to start with. And we want to talk about compound interest. So once we have the formula, the question is, how can we use it? What does it give us? What comes out of this formula? That's what the warm-up question is about. So we're doing compound interest from a bank. And it's up to you if you want to get interest once a year, twice a year, or 12 times a year. So either every month or twice a year, sometimes called semi-annually. You can either use the formula and calculate which you think will be better, or you can just use your intuition and try to do it that way. So that's the warm-up question. I'll give you a few more minutes to do that. A quick announcement as well is that the homework on this finance stuff, so this Chapter 9 finance things with interest and so on, the homework for that is posted. It is due on Monday at midnight, the same time it's always due. There is an important difference, though. In the previous homeworks, I've either had a pool of questions and you get a random subset of that pool, or there's random numbers in the questions, which meant I gave you as many attempts as you wanted to do the questions. For Monday's homework, I'm trying something different. I took all the questions directly from the PDF that is posted on CourseLink with all the extra homework questions. So the questions on Monday are taken directly from there. The numbers are exactly the same. And that means if you want, you can go read the solutions to all the homework questions that are due on Monday. So the answers are already posted. You can read the answers. It's different than before. This means that if you want, I'm not recommending this, but if you could, in principle, just type in the answers and never think about the questions at all and get all the right answers. I hope you won't do that. I hope you will take the opportunity to try them and see which ones are harder or easier, and then go read the solutions. So it's a sort of a different approach. You guys can tell me if you like it or not, and then maybe you can change the homework for the rest of the term. So tell me what you think. Yeah. So you still have infinite attempts, but it will not tell you what the right answer is. So before, it would say, you got the answer wrong. The answer was 2. You can try again on a new attempt. Right now, it'll just say you were wrong. It won't tell you the answer. If you want the answer, you can go read the PDF notes. Yeah, it should tell you if you're right or wrong, but not the answer. And then you can look up the answer in the PDF notes. So it's a different approach. I think a lot of people, probably people will do better. I'm hoping that by having the solutions written out, you guys will appreciate that and get something out of that. OK, any questions or comments about the homework or anything else? OK, so let's go over. I'll leave this open so you can keep doing this. And again, you can use your intuition or not. I'll take it off when we finish. Let me turn this timer off before it annoys us some more. We want to develop this compound interest formula. OK, and I'll wait a second until people stop talking. Thank you. OK, so we're trying to do this compound interest formula. And the whole shebang here, the whole picture, is in this little calendar that I drew. So in January, we put some money in the bank. The amount of money we put in the bank is P. So in this little row over here, I have the amount of money. And then we wanted to calculate what happens to our money throughout the year, assuming we get interest 3 times a year. So we're going to get interest once in May, once in September, and once at the end of December. So 1/3 of the way through the year, 2/3 of the way through the year, and all the way through the year. And we want to calculate our money over time. So we did last class, we did the first one. We did how much money we have in May, and we came up with this formula, P times, open bracket, 1 plus R over M. How did we get P times 1 plus R over M? It was the sum of 2 terms. It was P, that was the amount of money we started with, and then P times R divided by M is the amount of interest we got just from January to May. And it's R divided by M because that is the per period interest rate. So in just from January to May, you don't get the full interest rate R. R is for a full year of interest. We didn't do R. We did R divided by 3, 1/3 of the year. That's why it's R divided by M. That gets multiplied by P. This is the amount of interest we got just in that period. And if you combine these 2 terms and factor them together, you get P times 1 plus R divided by M. This 1 is coming because when you take a P and you factor out P, you're left with 1. So P times 1, P times 1. So that was calculating how much we had in May. And last class I said repeat the pattern, but I'll do it a little more slowly this time. That's catching us up to where we were last class. Any questions or comments about how we got this P times 1 plus R divided by M? OK, so now we're going to calculate. That was how much we had in May. How much did we have in September? I said you repeat the pattern. You multiply by 1 over R plus M. But let's do it more slowly and see why that's true. So how much money do you have in May? You had P times 1 plus R over M. That's how much you started May with. And then we do interest at an interest rate of R over M. Right? So we do the interest rate of R over M on our new account balance. And our account balance is this thing, right? P times 1 plus R over M. So we get P times 1 plus R over M plus P times 1 plus R over M. This is the amount of money in our bank account. And then we multiply by the interest rate R over M. So altogether, it's a sum of two terms. Both of them involve P times 1 plus R over M. That is how much money we had in May. And the second term is multiplied by R over M on the outside. And now again, just like I did in the first interest period, I can do a common factor of these two terms. And the common factor is exactly the thing in blue, P times 1 plus R over M. So if you common factor, P times 1 plus R divided by M, you get P times 1 plus R divided by M times something. To make the common factor really work, you should think of the first term as being multiplied by 1, right? It's P times 1 plus R over M times 1. So when you common factor out that P times 1 plus R over M, it's a 1 plus R over M. So I'll do that in pink to match that over there. So it's another 1 plus R over M. And now you notice you have 1 plus R over M twice. That is exactly this P times 1 plus R over M, all to the power 2, all to the power 2. There's a 1 plus R over M coming from the first interest period in May, and there's another 1 plus R over M from this funny factoring that we did. So the pattern is, to go from one period to the next period, you always multiply by 1 plus R over M by doing this factoring thing. Let me freeze that on the screen while I go to the next page. So on the next page, we're going to calculate what happens in the next month. And again, you can do it as a sum of two steps. Right? It's P times 1 plus R over M squared. That's how much we had in our second period, right, in September. And then we get simple interest on that, plus P times 1 plus R over M, again, times the interest rate R over M. Right? So to go from September to December, you're doing this calculation again, how much money you had, plus the interest on that money. And I forgot the very important term, the squared. Right? So this whole thing in brackets is the same in both. That is how much money we had in September. And then now we calculate how much we had. We add on some amount of money to get what we had in December. And again, one more time, it's the same common factoring trick every single time. There's a secret 1 hiding here. And if you put that in, you get 1 plus R over M factoring out. Which, again, the 1 plus R over M, you can put in the exponent, 1 over R over M cubed. And that matches what I put on the calendar, 1 plus R over M cubed in tiny letters in the corner. So to go from one period to the next period, we're always multiplying by 1 plus R over M cubed. How much money? We're always multiplying by 1 plus R over M. In 3 periods, we've gotten it 3 times. In 1 year, what did we get to? In 1 year, you're going to do it M times. So 1 year means M times. So what is the pattern? The exponent is the number of times you do it. So after 1 year, it's going to be 1 plus R over M to the power M. You're going to do it M times. And if you do it for t years, you're doing it M times t times. So after 1 year, it's 1 plus R over M to the power M. After t years, it's 1 plus R over M to the power M times t. You just keep doing it t times. In t years, you're going to do it t times M times. OK, and so all of that is to say, we have gotten to the formula that is in the book already, which is telling you the value of compound interest at some time t in the future, the amount of money in your bank account. And the big deal is that it's exponential in t instead of linear in t, like the simple interest. OK, that was a lot of deriving. We got to the final answer. We're going to work with the final answer now. But any questions or comments about the derivation or anything like that along the way? OK, so we have a bunch of symbols on a page. And of course, symbols on a page are good because they're right. But are they useful? You have to think of some problems and try to get into the spirit of things, which is why I gave you this fun problem, which is totally made up, but nevertheless will be useful to us. Why is this problem totally made up? Well, first of all, I only have $1 in the bank, which is a little silly because the bank would immediately take my dollar away as some kind of fee, and I would owe them money. So don't put $1 in the bank. It's a bad idea. And here's the other extra silly thing that you know it's a made-up universe. The bank is giving me an interest rate of 100% per year. There's no bank does this. This is a ridiculously generous interest rate. Normally it's a lot less, but just to make the numbers simple, we're going to do 100% interest per year. And it's up to you what M is going to be. So I have put in the principal amount, P is $1. I've fixed the interest rate as 100% per year. We're going to do it for 1 year. So T is 1 year. So in our equation, the only variable that I haven't done yet is what is M. And the question I asked you guys is what should M be? What is the best value of M? Someone in the front row said, it depends on your principals. So I'm assuming you want to maximize your money. You're not trying to give money to the bank. We're trying to take money from the bank, guys. Okay? We don't like the bank. The bank is the bad guy. So how do we get the most money? What should we do? And let's see what you guys said. All right. So there was options for 1 time, interest once a year. Interest 12 times a year, that seems popular. Interest 2 times a year, also not very popular. But a big, really common one was it doesn't matter, all options are the same. So 20 people chose it doesn't matter, all options are the same. This was out of 80 people who answered. So about half the people are in calculated 12 times. And 20 people are in this it doesn't matter, all the options are the same. And this is a very tempting thing to think because if you look carefully, the interest rate goes down the more periods we do, right? So if you do it 1 time, you get a 100% interest. But if you do it twice, you get 50% interest twice. And obviously, 50% times 2 is 100%. So like 2 and 1 should be the same. 12, you get 100 times 12. 100 divided by 12 times 12, you're back at 100. So it seems like it should do nothing. This is a very tempting option. Let me draw a picture of this situation in Desmos that we will look at. And this is the Desmos version of what was drawn in my notes. But of course, the nice thing about Desmos is it's interactive and it does calculations. So this is supposed to match. Do I have the right page up in the notes? I don't. This, OK. So we had this little calendar in the notes, January, May, September, December, and I drew a picture of that in Desmos. So here it is in Desmos. We have the start of the year, we start with $1. At the end of the year, we end with $2 right now, because it's 100% interest, and right now I have set M equals 1. So this little slider over here for M is the number of times we get interest. So if you get interest 1 time, of course you get $2, 100% interest on your original $1. And the question is, if I change the M slider, does the graph change? Do we end with more money or not? And in Desmos, it's very easy to find out the answer. You just got to slide the slider over. OK, so let's do it. I'm going to take the slider for M. I'm going to slide it from 1 and slide it up to 2. And look at what happened. Look at what happened. So let me zoom out a little bit more. So we can see this is the graph now. Before we ended at $2. Now we're ending at $2.25. Why are we ending at $2.25? You can kind of tell yourself a little story here. You see, in the first 6 months of the year, the first half of the year, we gained 50 cents. This is the point 0.5, 1.5. We got 50 cents on our $1. And now we have $1.50 in the bank. And in the second half of the year, when we calculate interest on our $1.50, now we get 75 cents of interest. And so the jump, the second jump, is bigger than the first jump. So the total of the 2 jumps is bigger than it was when it was only 1 interest period. So the reason we're getting more money from the bank is because we're getting interest on our interest. There's interest on this little jump that is added on here, and we're ending the whole year 25 cents richer than we would have been. So 2 is definitely better than 1. So if you selected the 2 option, if you selected the 1 option, you're definitely wrong. 2 is better than 1. Is 12 better than 2? So let's slide the slider over and see, does it keep going up? So here is 3. Here is 3. That's like what I had in the corner of the notes, right? 3 pay periods. So in May, you gained a little bit of money in May, then you gained more money in September, and you gain even more in December. And going up again, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get more and more money. You end the whole year at $2.61. So you're sort of 61 cents richer than you would have been if you had taken just 1 payment. It is better to take 12 payments than 1 payment because you get interest on your interest. This is the whole shtick in compound interest is interest on your interest. You want to do that as much as you can to get the most interest on your interest. OK, so the right answer is 12, and we saw it in Desmos. Any questions or comments about this example? I'm trying to illustrate the equation visually, right? So the equation is sort of like boring. It just looks like this. To understand what the equation is doing, I made this nice Desmos thing to show us how it changes when you change m, which is the new thing, right? The number of pay periods is the new thing compared to simple interest we were doing last class. Questions or comments about that one? OK, so if there's no questions or comments, I'm going to ask you guys a question. We got up to 61 cents stolen from the bank, 61 cents in extra profit, but I'm going to be a greedy guy, and I'm going to go for a full extra $1. So we saw by the magic of compound interest, the more times you do interest, the more money you get. So instead of getting just $2, we can get more than $2. How many times do we have to compound to get $3? So far we've gotten to 2.61 with 12. How big does m have to be for me to get a whole extra $1? I want my extra $1. So you guys tell me what you think. You can either use the equation and try to figure out, or you can just do your gut feel. So the point of this question is just to give us a sense of what's going on for different values of m. So you can plug in some stuff. You can try it. The link to the Desmos is also in Math1030 on the previous question. So you can use that as well. Or you can just take a gut feel. Do you think it's going to be 10, 100, 1,000, 100,000? What do you think it's going to be? I'll give you 2 minutes to work on this one. Actually, if we're going to go by gut feel, let me just give you 1 minute. You can give me what you think. OK, so in 1 minute, we'll come back together, and we'll take it up. OK, 10 seconds left. I think there's like 20 people who still haven't put in an answer. So put in a guess. What are you feeling? Do you think it's going to be like 10 or 100? How big is it going to have to be? OK, so let's look at what people said. Oh, and I think the timer was trying to start again. Let's stop the timer. OK, let's see the results. OK, so 10, if you chose 10, 10 is the only one you can be sure is not enough, because in Desmos we did 12 and we only got to 2.6. So 10 is definitely going to be less than 2.6. 10 only gives you 2.59. 12 only gives you 2.6. It's definitely bigger than 12, or bigger than 12. Is 1,000 enough? 13 people picked 1,000. So we can go into Desmos and we can say, let's see 100 first. Was 100 on there? 100. 100. Most people picked 100. Let's see if 100 is enough. So that would be like getting interest every 3 days, right? A year is 365 days. Twice a week, something like that is 100. So let's see what we get. We're getting more and more interest. You see the jumps get smaller and smaller, but there's more of them. We're getting more and more interest. It's going up, 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 up. 50, 70, 80, 90. After 100 times of getting interest, you're only at 2.70. Only at 2.70. So 100 is not enough. If you chose 100, you were not right. Is 1,000 enough? Is 1,000 enough? Again, we got to ask Desmos. Please go up to 1,000 now. OK, and we started at 100. Now we're going up faster and faster. 400, 500, 600, 700, 800, 1,000 only gets you to 2.716. So going from 1 to 2, from 2 to 12, that was a pretty good jump. We gained an extra 60 cents. But going from 12 to 1,000, we've gone up from 2.6 to 2.71. Only an extra 10 cents in those next 1,000 things. So the bank is like giving us interest 3 times a day, and we're still barely making any extra money. OK, what was the next option? The next option was 100,000. 100,000. Only 3 people picked 100,000. Let's see what happens if you go all the way up to 100,000. And there's a chance my computer will catch on fire and Desmos will crash. We'll try it. 100,000. No comma. OK, here we go. 100,000. Nah. OK, so it looks like if you do 100,000, you don't get to 3. You don't get to 3. You get stuck at the stupid number 2.7182. 2.7182. So the right answer was, there is no way You will never get above $3. Even if you compound every microsecond all day long, the more you compound, you will never, ever get to $3. The highest you can get to is 2.718. Let me read more decimals. 2.718268. Does anybody recognize the number? Put your hand up if you've seen this number before. 2.718268. Put your hand up if you've never seen this number before. This is a new number for you. Okay, you guys are in for a treat. This is a special number. Just like when you're a kid and you learn about pi and you get really excited. Okay, I don't mean the like sweet, delicious treat. I mean like the circle pi. Did everybody do this when you're a kid? You like measure circles and you like do the ratio of the circumference to the radius. You got to do like 10 circles and you're like, oh my god, it's always 3.14. This number is the pi of calculus, 2.718. This is Euler's number. Let's do a Google search. Euler's number. So Euler is a famous German mathematician, and he has a number. Look at this. Number file video is the first hit. E equals 2.71828. That is exactly the number we found. That is exactly the number we found over here. I think of E, one way to think of it is the compound interest number. If you are doing continuous compound interest, doing compound interest every microsecond of every day, you're going to get to E dollars in this setup. Not 2. 2 would be simple interest. You get a little more than 2, 2.7, because of the continuous compound interest. It's not quite 3. You can't get to $3. That's impossible. But you can do 2.718. All of this stuff is in your notes. So we're going to skip forward a little bit here. These exercises, exercise 167, these were all extra videos. They've been posted already. And we're going to section 9.3 on continuous compounding. And everything that is written here is a mathematical derivation of that picture proof I showed you in Desmos. That says that the more times you compound, the closer and closer you get to some kind of something with the letter E. And the final result, the most important result, is this one with a star at the end. So this is a proof using limits of what we saw visually in Desmos. So this is like an algebra proof. I showed you guys the picture proof. I think the picture proof is more helpful for your understanding. We finally get to this formula 26, which says that if you deposit P dollars and you're getting an interest rate of R% per year, then the formula for how much money is in your bank account when you compound continuously involves the letter E. So the letter E sort of comes out of nowhere from this fact that you're doing continuous compound interest. And even though there's no E anywhere at the bank never calculated 2.718, there is an E in the formula because it is the magical thing that comes out of this process of continuous compound interest. And the formula is A equals P e to the RT, right? So this is continuous compound interest. Let me put all the formulas together. Compound. The other formulas we had were this one, 1 plus R over M to the power M times T. This was regular compound interest, regular compound with M periods. And we had this formula for simple interest. That was way back at the beginning of the chapter, and it was I equals P times R times T. So the compound interests, they're both exponential, and the continuous compound interest involves the letter E. E comes out of nowhere out of this process of continuously compounding. This is the same reason, by the way, in what chapter was it? When we did exponentials. I think that was chapter 7. Chapter 7.4, we did exponentials, and there were all sorts of problems that said bacteria are growing in a petri dish, the rate of growth of the bacteria is so much, and the answer involved E, right? And the notes just said it involves E just because. Now you know why just because. Bacteria do the same thing as continuous compound interest. They're always dividing. They're continuously dividing, and that is why this E thing comes up everywhere. Anytime you have a process that is naturally happening all the time, like bacteria growing, or another example is atomic nuclei decaying, it's going to involve the number E for the same reason that banks that do continuous compounding involve the letter E. Later in the course, we're going to see that this E thing has a very nice interpretation in terms of calculus. So calculus is all about how things are changing, and this E function is the special number that is changing in a nice way. It sort of has the right growth rate that matches the value of the function. We're going to see that later in the course. So this E thing is magical. If you've never seen the number 2.718, you're in for a treat. I think it's just as exciting as pi, if you ask me. Okay, we're going to go on to a question. I'm going to ask you guys a question, but this is a really good point to stop. If there's any questions about this big picture stuff with E, or the difference between the continuous and the simple interest, or anything like that. OK, I can tell you guys are dying to do the question. You want to do the question, that's why. So we're going to do exercise 170. There's a bank, and they're offering continuous compounded interest. You put in $2,000 at an interest rate of 2.85%. I would like you to find the balance after 3 years. I'm going to give you like 2 minutes to work on it. And then I will put up the multiple choice answers in Math1030. But I'm only going to give you like 30 seconds to answer after I put the answers up. So try to do it on your own. Try to get an answer on your page. And then you'll just match the answer to my multiple choice, OK? So I'm going to give you 2 minutes to do that. OK, so I'm opening up. It's been 2 minutes. I'm going to open up these 4 options on Math1030. You should have one of the 4 on your page, including none of these as an option. So choose whichever you have written down. And I'm only going to give you 30 seconds. So you don't have enough time to reverse engineer the problem here. But you have enough time to match whatever you have written. OK, let's take a look at what people said. Let's see what people got. OK, so 5 people in this answer. The first answer written there is the correct answer to the question if it was simple interest. So if it was simple interest, that is 100% the right answer. The question was saying continuous compound interest. So it's the wrong answer, but it's the right answer to a different question. So if you selected this answer, you were probably thinking of simple interest. That is what we did last class. The interest you get is $2,000 times the interest rate 0.028 times 3 years. And then you add that on to the $2,000 you had to begin with. If you selected this answer, this third answer that only 12 people selected, then you've done something in between simple interest and compound interest. And I think the way you can tell for sure something is wrong is where is that value of t. So in this case, t is 3 years, and you're putting the times 3 at the end. So presumably, if it was 6 years, you would do times 6. If it was 12 years, you would do times 12. If you're multiplying the whole thing by 3, that is linear growth. So simple interest and this equation over here, they're both linear. If you double the time, you double the amount of interest. And that is not what compound interest does. So this one for sure is wrong because it is not growing exponentially. It needs to grow exponentially. Compound interest, the t is always going to be in the exponent somewhere. For continuous compound interest, it involves an e, and for regular compound interest, it involves a 1 plus something. So it looks a lot like this should be the right answer. It's got e. The 3 is in the right spot. The most people chose it. Let's reveal the right answer. The correct answer is none of these, none of these. So if you were one of the 40 people that chose this one, there is a mistake. There is a mistake. I'll give you guys 1 minute to discuss. Talk to the people near you. Try to find what is the mistake. We're going to come back all together and we'll take it up.
Question.
Yeah.
Is the mistake, is this supposed to be 1.0285?
It could be. So yeah. It could definitely be that. Yeah. Why is it?
Because then it's like you're adding a whole percentage. So it's like 103% instead of just 3%. Maybe. Who knows? I think you're right.
Okay. So I'll wait for people to stop talking, and then we will take it up. Okay, thanks. So does somebody a brave volunteer want to tell me what is wrong with this thing? This is the wrong answer. There's a common mistake here. What is the mistake? Who wants to take a guess? Yeah. You don't add the first 2,000. You should not add the first 2,000. That is exactly right. If you just take this part of it and you delete the 2,000 plus, that is the perfectly right answer. And this is a common mistake people make. And again, if you compare it to the simple interest, in the simple interest, you should do the 2,000 plus. In the compound interest, you don't. And so this is a common mistake. I want to talk about it briefly and how I remember it at least. So we're going to do the solution. If it was simple interest, which it's not, but if it was, the answer would be $2,000 plus $2,000 times R times T. That's the simple interest way to do it. And the compound interest, and I'm going to say continuous compound because it involves the E, is $2,000 times e to the R times T. So you don't add a 2,000. A really simple way, this is how I remember it. If I ever get confused, I think of what happens at t equals 0. So this is the way I remember it. What happens at t equals 0? So at t equals 0, it's supposed to tell us the amount of money we started with. In the simple interest, if you put in t equals 0, this whole term kind of cancels away, right? It's r times 0, the second term, this term representing how much interest you got, that will be 0. So when t equals 0, in the simple interest case, it's $2,000 plus 0. It makes perfect sense. In the continuous compound interest case, you have an exponent of 0. And when you have an exponent of 0, you get 2,000 times e to the 0. So it's not that we're adding on 0, we have 0 in the exponent. And anything to the power 0 is 1. 2,000 times e to the 0 is 2,000, as we expect. If you added on an additional 2,000, it would be wrong. It would be saying that when at time 0, you had $4,000 to start with. That's definitely not right. So this is the right formula, and that is how I remember what is going on. It's important you keep track of this. So sort of the exponential already has this stuff built into it. Maybe I can compare it for the sake of comparison, and actually that'll be a good summary to the chapter as well. That was simple interest, continuous compound interest. Regular compound interest looks like this. It's $2,000, and then you do 1 plus r over m to the power m times t. And you can see the 1 plus is already built into it, right? The 1 plus is already built into it, and when we did the limit as m goes to infinity, this whole 1 plus to the power m is what became e. So e already has the 1 plus built into it. You don't add on an extra $2,000. So that's a really common mistake I see. That's why I wanted to point it out with that question. That being said, maybe I can finish the actual problem. if you put in the actual numbers, it's e to the, what is r? R is 0.0285. That's in units of 1 over years. You multiply by 3 years. In this case, the units all line up nicely. There's no issue. But if instead of 3 years you had 100 days, you got to watch out for that. We did that last class. And if you do this correctly on your calculator, you should get $2,178.52. That's another way you can sort of ballpark that things are wrong. In this problem, we got $178 of interest. If you did it the other way, you would have gotten $2,178 of interest. There's probably more interest than you think. Question up here, yeah?
So the reason I took something else that I used the regular compound interest formula.
Yeah. Yes, that's right. So in the question, the key word is this compounded continuously. So if a bank tells you they're compounding continuously, that means they're doing this thing of doing interest rate over and over and over again every microsecond, and that is where the E comes from. So your answer will involve the letter E. If they were saying, I do interest semi-annually, that means twice a year. If they say, I do it 12 times a year, that means 12 times a year. And then you use the other formula, and you know what M would be. So the other formula would involve M. If there was an M in the question, that's where you would do it. There's a couple examples like this posted on the extra videos that you can go check out. That's a great question. And I will say for banks, it will tell you straight up. For other questions in the course, it might say bacteria is growing, and you just have to know that bacteria grow continuously. And it involves E. So we did those before in chapter 7.4, and we just said, just like chill out, we'll tell you where the E comes from later. Today's the day we're telling you. So watch out for that. Even though the question didn't involve E, the question has the E in it through this mechanism of continuous compound growth. Okay, great question. Any other questions or comments? So that being said, if we do part B of the question, how long would it take for the money to double? Part B is an exact identical question to those questions from chapter 7 about how long it takes for things to double. The answer involves the ln of 2. Involves the ln of 2. Right? We saw those. They involve the ln of 2. The ln coming because we have exponentials base E. And this one is identical to what we did in chapter 7. The main idea I want to show you guys today was this exponential growth, where E comes from. So I'm not going to do this one. We'll leave that as an extra video. Okay. And that is it for chapter 9. So chapter 9 has another section called effective rate of interest. This is just repackaging what we already did in a new way. I'm going to skip this. I won't ask you about effective rate of interest. It's enough for you guys to know these 3 things. So I think this is actually a really good summary of the things in chapter 9. There were simple interest, compound interest, and continuous compound interest. And you see the 3 formulas there and how they're different. One of them is linear. The other one is involves this 1 plus M, and the other one involves an E. That's a good summary of the whole chapter. Any questions or comments about that before we move on to chapter 10? All right, so we're going to move on to chapter 10. Chapter 10 is where things get exciting in this course because it's going to, all right, so I got to open up a whole different file. Chapter 10 is exciting because it's going to combine different parts of the course. So at the beginning of the course, we did all this stuff with functions, and we had domain and range, and we learned about different functions and how do you combine them. And then we did a detour, and we did sequences and this exponential growth stuff and things like that. We're going to combine them to understand what a limit is. So a limit combines the idea of functions and knowing what a function is. A function is a machine with inputs and outputs, and also this idea of getting really, really close to something like we saw in sequences. And the first little paragraph here is warning you that functions with real domains, like functions like we've been looking at, they have more complicated limits. So the limits for functions, and specifically I mean functions with inputs and outputs that are like real numbers, like f of x equals y. This is harder than limits for sequences, like we saw. Limits for sequences. And why is it harder? In the last 10 minutes, I'm going to give you guys a warm-up problem that is not in the notes, but it's a warm-up problem to try to show you what is the difference between limits for functions and limits for sequences. So it's going to be in Mathematize over here, and it's what I call this warm-up thing. And we have a function, our favorite function, f of x equals x squared, the squaring function. So we're back into function land. F of x is x squared. But now there's going to be two sequences floating around. So far in the course, every single problem has involved at most one sequence. This problem has two sequences. We're going to have a sequence of x values. I'm going to call it xn. So you can imagine xn is one of these geometric sequences or arithmetic sequences we saw. And we're going to make a new sequence of y values. So we take our x value sequence, somebody gives that to us, and I shove it through the f machine, and I'm going to get a sequence of y values. So yn is f of xn. And in this case, the function f is x squared, so it's xn squared. So we have one sequence. We make a new sequence. We have x's and y's both floating around. Here is the question. That was all just set up. Here is the question. If xn has a limit of 2, so the x's get closer and closer to 2, what can you say about the y's? So the x sequence is getting closer and closer to 2. We shove them through the f machine, the squaring machine, and we want to know, what are the y's doing? What is the limit of the y's? So in one sentence, if the limit of the x values is 2, what happens to the y values? And there's all sorts of things that can happen. I gave you some options here. Is the limit 4 no matter what? Is the limit 2 no matter what? Or maybe it depends on exactly what the x's are doing. I was pretty vague about the x's. I just said the x's are going to 2. And to help you guys out, I drew a picture in my favorite Desmos, of course. So y equals x squared is that blue curve. Maybe I can make it a little bit bolder. Let's make it a little bolder. There we go. And I have the line x equals 2 drawn as a dotted purple line there. And here is an example of what it would look like for the xn's to go to 2. Here is what the xn's going to 2 looks like. It might look something like this. So on the bottom over here, the x values are representing the xn's, and they're getting closer and closer to 2. And the y values are what happens on the curve. So you follow that dotted line. You look at the dot on the curve at that x value. That is f of xn. What are the y's doing? And you got to remember, this is one specific example of a sequence xn. In Mathematize, I want you to do an arbitrary sequence, right? It could be any sequence. The only thing you know about it is that the limit of the xn's is 2. So when the limit of the xn's is 2, they're getting closer and closer to 2. What happens to the y values? And that's the question. I'll give you 1 minute to think about it. Again, this is mostly a gut feel question, although I will say you have the actual tools to solve this one exactly. If you had an open book exam and this was the only question with enough time, you would eventually figure it out. There is something we did earlier in the course that lets you do this one. So I'll give you 1 minute to try that, and then we'll take it up. Feel free to discuss with your neighbors or put up your hand, and myself or Adrian can come around. Okay, like 5 seconds left. Put in your guesses if you haven't yet. Okay, let's see what people said. So again, lots of different answers here. We saw with sequences, there's a lot of things in general that can happen, right? Sequences in general, all sorts of crazy things can happen. What happens in our case? Okay, this is fantastic. Only one person thought the limit is 2. The limit of the x's is 2. The limit of the y's is going to be something else. It's not going to be 2. This is one of the confusing things about having x's and y's is sometimes you mix them up. So very good. Almost everybody didn't fall for this trap. So only one person mixed them up. 32 people said the limit is 4 no matter what. And that was what it looked like was happening for this particular sequence. So for this sequence, it definitely looks like the y values are getting close to 4. But the question is that going to be true for every possible sequence? Maybe there's a sequence out there where the x values, like, they go all wonky, they get close to 2, but the y values do something weird. Could that happen? And 29 people chose that option. That it might exist or might not exist, depending on the details. And 16 people said the limit of the y's will exist, but maybe isn't 4. So people are pretty split. Out of 78 people, we got 32 to 16 to 29 on these possible things. Is the limit always 4, or is it sometimes 4? Or is it sometimes not even existing? The correct answer is that it is always 4. It's always 4. The limit is always 4. And I said you have a tool in your toolbox of being able to do this. Earlier in the course, we talked about these limits, right? We're doing the limit as n goes to infinity of yn. That's what we want to do. And in this case, the limit is the limit of xn squared, right? Since yn equals xn squared. This is the problem that I gave you guys. Let me zoom in a bit here and over. OK. And up. OK. So we're doing the limit of xn squared. If you saw a limit of something squared, this should trigger in your brain the limit rules. We did limits of sequences, and we said if you know the limit of something, then you can find the limit of things involving that something. And one of the limit rules you could do, let me do it this way. Let's write xn as the limit as n goes to infinity of xn times xn. xn squared is xn times xn. So it's the limit of one thing, the xn's, times the xn's. What happens if you have the limit of the product of two things? One of the rules says that this is equal to. This is the product rule for limits. Product rule for limits is the limit as n goes to infinity of xn times the limit as n goes to infinity of xn. So the product rule for limits says if you're multiplying two things and you know what each guy individually does, you can do the product. We did that in the course. That was, again, it was before the finance stuff, so maybe a little rusty in your mind, but also quite recent. And the limit of the xn's we said was 2. So this is 2 times 2, which is 4. So the limit of the y's is going to be 4 just because of that product rule for limits. It's going to force the limit to be 4. And you can see that in the picture. Let me freeze this for people who are copying. You can see that in the picture that if you have some other limit, the only other really interesting thing it could do is sort of come at the limit from the other side. So the x's maybe could come down to 2 instead of going up to 2, but the y values would then go down to 4 instead of going up to 4. So if I zoom out a bit here, you can see they're still getting really close to 4, but from the other side. So this was an example where the limits kind of behave nicely. You have the x's and the y's, and you can figure out what the y's do in terms of the x's. In your notes, the very first example in the notes on the next page is this function, x squared divided by x minus 1 times the absolute value of x minus 1. This function looks like this. It looks like this. It's a function that has a big nasty jump, and it has holes on either side. Next class, we're going to do the exact same question we did as the warm-up question, but instead of doing it for the function y equals x squared, we're going to do it on this function. And we're going to see that something different is going to happen. Limits for functions have all sorts of nasty cases that don't happen for limits of sequences. OK, that's going to be next class. I'll stop there. I'll be here for a few minutes if you have questions. Otherwise, see you guys on Friday.